So I got a comment not too long ago relating the beginning of plate tectonics on Earth with crust formation on Earth. But actually there's a big difference between tectonic plates and Earth's crust. So in this video, I'm going to be talking about how Earth's crust formed and the difference between tectonic plates and Earth's crust. So we'll talk first about Earth's crust and the difference between oceanic and continental crust. Then we'll move on to how Earth formed and then how crust formed on Earth and how it differentiated into oceanic and continental crust. And then we'll talk about the difference between crust and tectonic plates. So I talked about this a little bit in my recent Earth's Age or Dating Earth video where I talk about the oldest oceanic crust versus the oldest continental crust. Basically, oceanic crust is formed at mid-ocean ridges or oceanic spreading centers where new crust comes out from the mantle because the tectonic plates are being pulled apart, allowing that to happen. But because this new crust that forms oceanic crust is more dense than the buoyant continental crust, it becomes subducted under continental crust over and over again and recycled back into the mantle and then plumes back up through mid-ocean ridges. And because of this constant recycling, the oldest oceanic crust is only about 260, and I've also even seen 200 million years old. The point is that it's much younger than the Earth, which is billions of years old, whereas continental crust is preserved for a lot longer because it's too buoyant to subduct. The oldest continental material ever dated is about 4.4 billion years old, but still, this is not even as old as the Earth, which is about 4.55 billion years old. Why does the oldest continental crust, which doesn't subduct, not equal Earth's age? Well, Earth wasn't born with crust. In other words, it didn't accrete and immediately have crust. It took a while for crust to form and cool, and also to differentiate into oceanic and continental crust of very different material. Oceanic crust is very dense and more mafic, meaning just contains more dense elements like iron and magnesium, whereas continental crust is a lot more buoyant and more felsic, containing a lot more silica and less of those dense materials. And so it's very different material, and this took a long time to not only form but also differentiate into these two major types of crust that we have on Earth today. If you want to know more about how we actually got the 4.55 billion year estimate for Earth's age, you can watch my How We Dated Earth video. But for this video, let's talk a little bit about how Earth formed or accreted, and then how the crust finally formed. So like I've mentioned in a few videos, the solar system formed after a supernova or star exploded, and you had this nebula of material spinning around in space, which then started to accrete, or material from that nebula started to accrete to form the planets, as well as the sun in the center of it. And on the rocky planets, or the inner planets like Earth, you had material with pretty heavy elements like iron, magnesium, and silicon collide and accrete. And the accretion process was held together because of gravity after it got to a certain size, and then more and more accretion happened because it had more gravity and it pulled more material into it. At that point, Earth was very hot and molten because all of those impacts were providing heat and energy, so it wasn't like a very cool or solid material. It was very molten and active and still having much bombardment on it during this time in the Hadean eon, which went from around 4.55 to 4 billion years ago. And three main factors contributed to the heat of Earth at this time. These three factors included, of course, impacts or bombardment, as well as gravitational compression and radioactive decay of isotopes. So I've talked in the Earth Age video, as well as my stable versus radioactive isotope video, about the decay of radioactive isotopes or unstable isotopes that also releases heat to Earth through time. And so during this point, it was a lot of decay. Now that we've gotten, 4.55 billion years into Earth's lifetime, there's less radioactive decay, but it's still going on because some radioactive elements or isotopes decay much slower than others. However, it did eventually start to cool down, and as it did, it differentiated into different layers. If you've ever seen a cut of Earth, kind of like this one here, you've seen that Earth has layers. We know Earth has a solid inner core, liquid outer core, a mantle, and crust, and those layers formed because the dense elements, as it was very molten at the time, sank to the core, and the less dense elements rose to the surface or just toward the outer layers of Earth, and this is what led to the layers we see today. So we see less dense silica-rich material towards Earth's crust and upper mantle, and more dense iron-rich material in Earth's core. And the formation of Earth's liquid iron outer core led to the magnetosphere, which has protected Earth from harmful solar radiation and solar wind throughout its lifetime. And this has allowed, things to live on Earth. Without the magnetosphere, it would be an extremely harsh environment to be on Earth. So how did Earth's crust actually form and differentiate into both oceanic crust and continental crust? Because if you think about it, there's not a special mantle providing material to the ocean versus the continents. They're very different materials, but they came from the same source. So how did that happen? Well, first on Earth, the very initial crustal formation on Earth was a very heterogeneous oceanic crust. However, plate tectonics got its start early and was faster on early Earth because Earth was so much hotter. Now, I want to put a little disclaimer here that there have been debates of how fast plate tectonics really was on early Earth. Was it really faster? But in general, we would expect that due to the intense heat in the mantle at the time, we would have expected intense convection and therefore very intense and rapid plate tectonics. But just disclaimer that there's research going into pretty much everything I say on my channel. So don't think that I'm just saying that this is the way it was. There's plenty of different hypotheses, but this is, one of the major ones. And because of this rapid and intense plate tectonics at the time, crustal differentiation occurred. And so what does this mean? Well, partial melting of this heterogeneous material that had formed on early Earth led to the purification of oceanic crust and the formation of the first continental crust about 4.4 billion years ago. So what does this mean? What is partial melting and how did it differentiate these two types of crust? Well, partial melting is when only part of a solid is melted, so that makes total sense. Part of the solid melts and part stays behind. This has been happening on Earth for a very long time in Earth's mantle, and that leads to the melted part of the material, the solid from Earth's interior, rising through Earth's crust, coming out of volcanoes and actually forming new material at Earth's surface. The stuff that doesn't melt fully stays behind in the mantle and doesn't come and form stuff at Earth's surface. This is important because felsic material melts at lower temperatures than mafic material. In other words, if we look at this figure to the left, we see that this heterogeneous material on the left of the figure begins to melt, and because of partial melting, or because felsic material, the pink and white material, melts at lower temperatures than the mafic material, it will melt and rise and exit the system or exit the mantle, whereas the mafic material will stay behind as residue because temperatures don't get high enough, or typically don't get high enough, to melt all of the material that's in that particular magma chamber or whatever it might be. So some very mafic material is always left behind, and the melt is always more felsic than its source. That leads to, over time, more and more felsic material being what comes out at Earth's surface. And so now we can see why at present day, at mid-ocean ridges, kind of mafic, dark, basaltic, or gabbroic material is formed at these ridges to form oceanic crust, because the melt is coming from a more ultramafic source. And ultramafic, if you don't know what that means, is just something more mafic than mafic. So basically, because the source is ultramafic, the material coming out of the mid-ocean ridges is mafic. Whereas when you have a subduction zone, The plate that's subducting is an oceanic plate. It brings down water with it because that material was hydrated when it was at the surface, it being oceanic crust, and it brought down that water with it, causing the melting temperature of that material to lower, and then it causes melting when it gets to a certain depth that reaches a certain temperature. And the melting of that material, because it's mafic instead of ultramafic, it causes more felsic material to form. And over time, this has caused more and more felsic material to come out of volcanoes at subduction zones, and that has caused continental crust to be much more felsic than what comes out at mid-ocean ridges, which is straight from the ultramafic mantle source. But this is a present-day scenario. How did this initially happen? How did continental crust even start to form from the heterogeneous monolithic crust that was initially formed on Earth? So step by step here, we're going to go through basically everything that was happening on early Earth that caused the buildup of continental crust over time. First and foremost, we obviously had oceanic crust forming at mid-ocean ridges that rose from mantle material, just like we have today. And we had remelting of this crust at subduction zones. Now, initially, the plates that had formed were kind of like ocean and ocean plates. And at ocean convergent zones, or zones where ocean plates are pushing together, there can be subduction of one oceanic plate under the other. So that's kind of what was going on in this heterogeneous monolithic time. And you had the subduction. And when you had the subduction, you got the partial melting that caused a little bit more felsic material every time you had subduction and melting of that subducted plate, because that subducted plate represented already partially melted and kind of fractionated material that was slightly more felsic than the mantle source. And so that melting caused more felsic material to come out, and then that felsic material was again partially melted because the next time something subducted under it, it went through that material and again went through partial melting through that zone, as we can see in this part labeled A here in the figure. So everything going through that zone of more felsic material is again becoming more felsic as it partially melts that material and then eventually comes out at Earth's surface. Again, everything becoming more felsic over time. This led to the purification of the initial heterogeneous oceanic crust because it was releasing all of its felsic material at these subduction zones, forming these masses or pods of initial continental crust that started to not only form but accrete onto each other because you had these pods of continental crust that then headed toward each other, and as they head toward each other, they closed oceanic basins because the oceanic crust would subduct underneath them because they were much more felsic and more buoyant. And so as the oceanic crust subducted beneath them, they then met up with each other, as we can see in the bottom part of the figure here, where they met and accreted onto one another, and that just formed a larger pod or mass of continental crust. These masses of continental crust were forming throughout early Earth's history, and by around 2.5 billion years ago, 80% of continental crust that is on Earth today had formed. Since then, the last 20% has been forming slowly by subduction and accretion over time. So in short, partial melting, or the formation of more felsic material at subduction zones, led to the differentiation of Earth's crust into both oceanic and continental crust. Just to round out the picture a little bit, so you know what else was forming on early Earth at this time, you had the atmosphere being developed by outgassing, or gases being extruded from volcanism at the time, because again, volcanism was rampant because things were so hot, especially right after Earth had accreted. And so because you had this volcanic outgassing, they were pouring out these gases into the atmosphere, or forming the atmosphere with these gases, such as nitrogen, carbon dioxide, methane, water vapor. Oxygen was something that came later due to the evolution of photosynthesis. And because it outgassed so much water vapor from the hydrated rocks that had accreted to form Earth, this water vapor then eventually cooled and condensed after Earth had cooled below the boiling point of water to form Earth's oceans. And we also got a lot of water from comets that contained water and impacted Earth, but part of it was because of the volcanic outgassing of water vapor from the hydrated interior of Earth. So now that we've talked about how Earth formed, how Earth's crust formed, how Earth's crust differentiated into oceanic and continental crust, let's talk a little bit about the difference between crust and plates. Because from my discussion, I mean, even I use terminology that makes it sound like crust and plates are one and the same because I say oceanic crust subducts under continental crust, but it's really not crust that is what plates are made of. It's actually lithosphere. So if we look at this figure over here of this cross section of Earth, we can see the inner solid core, the outer liquid core, the mantle, which makes up all three of the next layers because we have like the lower, the middle, and the upper mantle. And then we have the crust, which is this brown and green stuff. Not to scale, I should mention. The crust is actually way thinner than, for example, this upper part of the mantle. So keep in mind, this isn't necessarily to scale. I'm going to show you one in a second that should be a little bit more to scale, but the gist of this figure is just to show that the crust is the outer part, and the lithosphere actually includes both the crust and the uppermost part of the mantle, this brown mantle layer here. And that is what makes up the broken up plates that undergo tectonics on Earth. So now if we look at this figure over here, we can see a bit more of a clear explanation of what's going on here and a little bit more to scale as well. We have the outermost part of continental and oceanic crust here. Again, oceanic crust is much thinner than continental crust and denser, which makes sense in this figure. And then we can also see the lithosphere, or the lighter brown part here, is not part of the crust. It's actually the uppermost solid part of the mantle. Why, do you ask? Do we not just make it simple and say lithosphere equals crust and just include all of the lithosphere in what we define as crust? That is because the boundary between the crust and the mantle is defined as the MOHO boundary. It has a longer, more official name that I'm not going to try and say because I've tried to say it in the past and it just doesn't work out. But anyway, the MOHO boundary is the boundary between crust and mantle. Pretty simple, right? So why does this matter? Why did we come up with this boundary? It is because that position, or that boundary, marks a distinct change in velocity of seismic waves that indicate a distinct change in material density. And so we have defined the density that we see above that boundary as crust material, and the density we see below that boundary is mantle. And so therefore the lithospheric part of the mantle must stay as being defined as mantle. But it is the lithosphere that makes up the tectonic plates. The point here is that lithosphere equals part crust and part mantle. And because tectonic plates are lithospheric, they can contain both continental and oceanic crust. So another way that it's easy to tell that it's not just the green things on this map riding along the blue stuff. It's actually all of that material broken up into deeper segmented plates. And because tectonic plates have been moving around on Earth throughout Earth's history, many supercontinents have formed as a result. And some of the major supercontinents that have formed throughout Earth's history include Columbia, which formed around 2.5 billion years ago and lasted to around 1.5 billion years ago. Rodinia, which formed and lasted from around 1.1 billion years ago to around 750 million years ago. Pangaea, which lasted from around 630 to 570 million years ago. And of course, the one we all know and recognize, Pangaea, which was kind of during the dinosaur era or before it, and then into the dinosaur era from around 300 to 180 million years ago. And it greatly contributed to the greatest extinction event of all time, the Great Dying. But supercontinents represent continental crust, not lithosphere, even though the lithospheric plates are moving around, causing supercontinents to form. So why then are supercontinents possible if it's not just continental crust that make up the plates? Well, it's because, if you remember, lithospheric plates can contain both continental material and oceanic material. And when they contain both of those and two plates containing continental crust are moving toward each other, the oceanic material will become subducted under one of those continental masses, and that will eventually close the ocean basin completely, and the continents will eventually meet. And when they do, you will have two continental masses right next to each other. Eventually, if all of those plates containing continental crust come together and close their ocean basins and connect in some sort of way, they will form a supercontinent with kind of a massive ocean around them. And then in the same or equal but opposite process, they can then separate and form ocean basins from new material coming out of a rift or an extensional tectonic boundary. And I mentioned that supercontinents, just like Pangaea, as well as Rodinia, and actually all of these supercontinents coincide with major climatic and even extinction events, such as Pangaea, which contributed to causing the largest mass extinction of all time. But you might now be wondering why supercontinents have such an effect on climate or life and all of that. So if you want to know more about how supercontinents have, throughout Earth's history, affected climate and life, I talk about that in my Earth history playlist, which I will pop up here on the screen for you at any moment so you can check it out. My favorite instance of a supercontinent having major effects on climate is Snowball Earth. So I will link my Snowball Earth video up here for you on the screen. It's a bit old of a video on my channel, so it wasn't the best production quality, but I love that video and the information in it because I just find Snowball Earth to be so cool. And I will see you guys in my next video. Thank you so much for watching. Bye.